Assalamualaikum to Dr. Nur Hafiza. Now I would like to talk about our introduction. In real life, signal like sound or data from sensors often have noise which makes them unclear. This noise can come from the broken parts, interference or the environment. To fix this problem, we use something component that called as a filter to remove the noise. In this project, we are using FIR filter and it is a type of digital filter that is safe, simple and works well. We write the filter using C or C++ code and can run it on the Arduino, which is a small, cheap computer used in many projects. Arduino can filter signal in real time like cleaning up the sound or sensor data. We also use MATLAB as a software that helps us design and test the filter before using it on the Arduino. In short, this project uses FIR filter with Arduino and MATLAB to remove noise from the signal and make them clearer.
So for the methodology, there are two flowcharts. The first one is for the Arduino. It starts with the Arduino setup. Then we initialize the serial communication to 9600 port. Then we initialize the sample buffer to 0 and the FIR coefficient to H7 and the time variable is set to t equals to 0 milliseconds. After that, we start with a shift buffer which moves all the sample to the left and store the newer sample at x5 and x6. So if there are enough sample, which is t more than 60 milliseconds, there will be an applied FIR filter which is y equals to summation of hi plus xi where I equals to 0 to 6. The output centered time will be 1 minus 60 over 100 and the noisy signal at center is x3 and the filtered value is y. After that, we have to wait for 20 milliseconds for a 50 Hz sampling and an increment of t by 20 and end of the Arduino coding. So this is the finished Arduino coding, which firstly we set up the number of samples, then the scalar buffer of past and future samples, and the time is converted in milliseconds. Then for the shift buffer, we do the newer sample goes at the end, and then we apply the centered FIR filter when enough sample is collected, and then we ensure enough past and future samples. Then the output centered time aligned to the center of the buffer, then the noisy signal at the center and ends with the 50 Hz sampling. So for the MATLAB flowchart, it starts with a set parameter to generate a signal and then set the parameter to define the FIR filter to simulate the data applying convolution on the filter. And the result will be displayed and ends with the desired graph and result. So this is the finished MATLAB coding, which firstly we set up the parameters and then we determine the sine wave which is 1 Hz and then we generate a cosine noise which is 10 Hz and the combined noisy signal with DC offset. Then we apply the FIR filter using the convolution with the same length as the input. The result will be plotted by the noisy signal and the x label will be time while the y label will be the amplitude of the graph.
Okay, now I'm going to show you how we execute our project by using Arduino Uno coding and also we use Arduino IDE. So before we start to implement our coding, so we have to choose our type of board and also port. So here our board is Arduino Uno and also we use COM12 serial port USB. Okay, so when we have setting that, we apply our coding and also same goes to MATLAB. We apply the sine wave and also cosine wave as the noise and we sum it, we can get the noisy signal. Then we plot the graph and also in Arduino Uno we can see the exact value of amplitude at 2.5 seconds. So when we compile and also upload their coding. You can see at the serial monitor at 2.5 seconds, the value before filtered is 502 and also after filtered is 506.57. Okay, now I'm going to demonstrate to you how we execute our project by using MATLAB simulation. So this is our coding, and as you can see here, this is our sine wave and also cosine wave that we use as a noise signal. So we combine and we create a noisy signal, which is the combination of sine and also cosine. And then we apply FIR filter and we plot the graph. So when we run the simulation, this is our okay, this is our result. As you can see here, the red one is the filtered value. And also the dotted blue line is our before the filtered value. So at 2.5 seconds before the signal is filtered, so the value will be 542. The amplitude will be 542, and also after the filtration, the value become 506.573.
Assalamualaikum and hi. My name is Wan Muhammad Shakir Ramadan bin Wan Azman. So today I will present to you about the result and discussion. So as we can see here, there are three methods that we use, which is the manual computation, Arduino implementation, and MATLAB simulation. So we need to compare the signal result from these three methods at the 2.5 second using FIR filter and without. So our aims is to assess the accuracy across method, detect discrepancies and validate results, and lastly, ensure practical reality. As we can see here, this is the three method comparison table about the before filtering and after apply the FIR filtering. So for the MATLAB, before filtering, we detect that noisy signal with large disturbance and random oscillation spike at 2.5 seconds and amplitude 542. But after apply the FIR filtering using the MATLAB tools, spike reduced to 506.573 at 2.5 second. That causes noise reduce. For the Arduino, before filtering, we get the raw sensor data show jitter, spikes, and instability at 2.5 second. But after apply the FIR filtering code in the C++ on Arduino, we notice that noise reduction at 2.5 second. And lastly, for the manual calculation before filtering, signal from theoretical sampling, inconsistencies and amplitude change at 2.5 second affect the sensor noise and ADC artifacts. But for this manual calculation, no post filtering apply to highlight that the challenge of analyzing unprocessed signal manually.
Although FIR filtering was effective across all three methods, it has areas for improvement. MATLAB offers idealized result but lack real-world integration, combining it with hardware via simulating and testing alternative filter like IIR or Kaiser. Along with adding complex noise model could enhance robustness. Arduino's limitation in fixed point math and processing power can be addressed by upgrading to more capable microcontroller like the TINC or ESP32. Using more precise sampling, optimizing memory, and importing filter coefficient from MATLAB or Python. While manual calculation aid conceptual understanding, they are not practical for real-world use, leveraging spreadsheet or symbolic tools with error tracking and boost learning. Overall, implementing a branch marking system using metric like SNR and RMSE improving visualization and blending MATLAB design strength with Arduino real-time capabilities will lead to better filter evaluation and practical performance.
And the last slide is conclusion. In conclusion, this project successfully show how FIR, finite impulse response filter, can effectively reduce high frequency noise from signal using both software and hardware. Using MATLAB, the team was able to simulate the filter and get the very accurate, clean result thanks to the powerful processing abilities. The Arduino was used to test the filter in real time, proving that FIR filter can also work well in small embedded system even with limited hardware. Manual calculation helped to understand the theory behind FIR filter, although the small differences were noticed due to the rounding. Overall, FIR filter were proven to be stable, reliable, and useful, especially in systems that need clear signal and in a steady phase. This project highlights how combining theory, simulation, and real-world testing give a complete understanding of digital signal processing. That's all from us. Thank you.